Hello, hello. Testing here. Microphone. That's almost good. Almost. Maybe, yeah. Just close it to my mouth, I guess. Yeah. Here I am. Time since I streamed the last time. I don't know. Yeah, so today, powder toy. Want to notify people. And I want to pull up the chat as well. Chat overlay. Nia. I'm still preparing stuff, you know. I mean, it's. Hey, you're here. Okay, I don't need to notify you then. You know them here. Okay, that's good. That's good. So I'm going to show what I can do with the powder toy. For now, just so you can see this stuff going, I'll show you something. Let's put a bit of water, run it. Here's the water, nice. And now let's put a bit of lithium into the water. I think I need more water. Hey, Yarmo, hello. By the way, I am on the on Mumble. If you want to come in and join voice, feel free. I mean, you will be hearable on a stream for sure. But yeah, just saying, in case you want. So yeah, you can put. What else do I need to do here before starting? No, I think that's all because yeah, I wanted to notify you too, but you are here already, so no need then to notify anyone. We have everyone already. Okay, so. So let me show you how this works. So for example, let's say we have titanium, okay? And with titanium you can make is the only element that you can make a box of, and it can contain the pressure. So for example, if I put water in here, right? Now here on the top you can see pressure minus 0.03. Now for example, let's say that we wait, okay, let me unmute myself. Hello, Yarmo.
Hello.
Okay, so I can put here a bit of lithium, and we heat the water and the pressure will rise. Okay. And the titanium is containing the stuff. Ah, you're always loud. Okay. I can make myself louder.
I need
Okay.
to quiet myself.
No. Or maybe, wait. What I can do is do it in my side. Maybe -6 dBs. Let's see. Can you talk?
Yeah. Here I am.
Wow.
Is that better? Is that better, Ollie?
Oh, it's still too loud. 12. Let's see. Try now.
Here I go again.
Ah, yes. Now that's better.
Awesome.
Okay, so now we have pressure here. If I open a hole, look what happens. Okay, doesn't seem to happen much. We are losing pressure. Now, you see? And now, let's heat it up more. So, now it's computing the pressure. And is exiting the hole, yeah, because of the different pressure. Okay.
That's so cool.
Yeah, it's quite cool. And also it computes the heat. So, for example, let's say that we have here a thermite. Which this burns very hot. Now we can put a bit of fire and quickly it has melted down everything. So let's put a bit more titanium here. A bit less of this, a bit of fire, and you'll see that now it's melting. Here the titanium is melting. And now there is too much titanium and it's not yet hot enough to melt it. Let's remove a bit more.
It's heating at the top.
And sitting at the top, yes, it has exited because of the pressure. And now it's sitting there on the top. So that's nice. Then, for example, let's see reactors. So I'm obsessed with the uranium reactors.
Yeah, I was trying to build one real quick, but I couldn't find all your materials. I didn't know what the yellow stuff was.
Yeah, so the basic stuff will be placing uranium. Okay. And then the uranium will activate by pressure mainly. Okay. Heat also helps, but it's basically by pressure. So it doesn't matter if I try to use fire here. I can use the fancy one. Fire, heat, fancy. Okay. Remove the grid for now. Come on. Yeah. Now. So I can even use fire. Try to heat it up. And no, it's not heating up. So it's not being activated. So to activate it, you need to enclose it in a pressured container. And now we need to increase the pressure of the container. So we use, for example, water vapor. Okay, and the pressure will raise because there is. So now you can see that the top right is increasing the pressure. Because the pressure is increasing, now the uranium will start also heating up. Now we have 1000 degrees, and now it's melting the titanium, and everything is melted. Fantastic. So it's producing so much output when you do this. Water vapor, that it's very hard to contain. You see that it's quite impossible to contain. There you go, there you go, there you go. Drop. And gone. And then in the process, let's say that we continue with this. We can even use rock. Like we build it in a solid ground, or we even can build it underground, so there is all around it. And you will see the shear force that this thing has. It's increasing pressure. And it melts through the rock. When it melts, it will lower the pressure, so it might slow down. Because the rock is not containing the pressure, it's leaking. So it's just slowing down. It still has a fair bit of pressure. Interesting that it's taking so much time to go through the rock. But yeah, it does very weird things. It's very hard to contain, as you can see. So yeah, other stuff that other people has done. More interesting stuff that I have seen. There is here deuterium. And I mean, if just in case we don't know what is deuterium, it's basically water with an extra proton, if I'm not mistaken. It's hydrogen with an extra proton. I think it says here. Oh, he's asking you if you are familiar, Yarmo, with this game.
No, not really actually. I think I've played it like a long time ago, but just like, oh, explosions, cool. But this is so much cooler now.
Yeah. Okay, this is the deuterium oxide, which basically is water where the hydrogen has an extra neutron. So this is a liquid. Okay, but it has something funny. It doesn't boil. It never boils, I think. So if I go with fire, it expands with heat. I'm not able to hit it fast enough like that. Let's just hit it like this. Ooh, I'm overheating the titanium. But yeah, it's growing in volume. As you can see, it's getting bigger and bigger. But yeah, that's mostly fine. But the interesting reaction is the reverse. So if we grab snow, ice, solid. No, it doesn't nitrogen ice. Can put it like that. Okay, and that will begin cooling the hydrogen. I can use even colder things. Is this freeze powder that will freeze everything? And now you can see that it's lowering the volume. It's getting smaller and smaller. Look, and now it's smaller and smaller and brighter.
Wait, why is the snow decreasing? The ice?
I think because it's being heated, I think.
Ah, okay.
And there are no walls outside, so that can be changed in the simulation here. We can put edge mode solid.
And what happened in the middle? Yeah.
The deuterium has reduced in volume, has been compressed to just that. So I'll fill it again, and now you'll see that it will be compressed again. You see? It's compressing now.
Yeah.
It's reducing to these small particles, and you can keep refilling this as many times as you want, and it will keep doing that. I mean, not forever, because it's counting how much there is. So every time it will be more and more deuterium, but it's small. I mean, there is the same amount as before, because if I expand it, you see, it recovers the original when it reheats. It recovers the original size. And now there will be like 3 doses of that. So if I heat it a bit, because now it's sub-zero, but if I heat it a bit,
what is going to happen?
Basically, it will no longer fit in the container. It will expand more, but it will not get the darker blue that it had before. See, now it's full, and it's getting compressed. So if I put a hole in here, it will just overflow. So it is a bit weird. But here comes the strange thing. So when this thing is cold, where it is? Where this thing is cold, let's cool it. Now my frames per second is 30 because there are too many particles that are moving. Maybe because of the display, we can do the nothing display, but no, still 30 frames per second. Okay. Which one it was? Heat, blob, fire, persistence. No, I want the fancy display. Where it is? This one. Okay, number 7. Can this visualize how Molotov cocktail works? Partially. I'm not sure. Soaking in cloth, that's not supported, I think. I haven't seen anything like that. Okay, now that this thing is so cold, it's storing a lot of energy. And now you come here and add a bit of protons, and it explodes very aggressively. And this is what is called a deuterium bomb. That, for example, we can load where it is. It's a nuclear plant. What could go wrong? So in here, so this is a proper nuclear plant that someone else did. You can try to use it for a second before destroying it. So we start it. Let's see. Okay. This on. Well, should be on. Primary loop. Ah no, down is on. So then here down is on, maybe. Control rods supposed to move that. Here it is beginning the change. Valve 1 open. Okay, everything is open. I don't know how this one works. But yeah, something is moving. I guess that at some point this will start. That's liquid nitrogen. Metal. Those are glow particles. Okay, I don't know how to use it, this one. Doesn't matter. I just want to destroy it. So we grab our deuterium. So I just put the simulation. Grab the deuterium. Grab the titanium. So just to contain it for a bit. Now we change. I think it's life to 500 will be enough. Do that. So that's the equivalent of having the deuterium totally cooled down to 0. And now we add the protons. And now look, frame by frame. Let's see. Heat, nothing display. Yeah, okay. So protons go. It's reacting. If we get heat display, okay, with the heat we can see it better. So there is a ton of heat, 9,000, 10,000 degrees here. It explodes through the shell. And now it's basically destroying everything. Here, you can see.
Holy shit.
Now there is a blast. Basically destruction. And almost everything disappeared. So I don't know, it's fun. They were also playing lately with the gravity bomb. Why didn't trigger? It was supposed to trigger already. Why it hasn't triggered? It's supposed to, or is because we are in negative pressure? There is something here that I'm not. Let's increase the heat pressure. It looks broken. It looks broken. Gravity bomb. No.
What is it supposed to do?
It needs Newton and gravity. That's it. That's it.
What?
Yeah. Wait. Again.
What was that?
I need to add Newton and gravity. Yes. Then you go. Add both. It compresses the space and explodes.
Wow.
There are lots of sort of destructive stuff here. Like, I don't know. The warp is an invisible gas that displaces stuff. Displaces pixels. I don't know. There is lots of stuff here. So yeah, that's more or less the basics here, no? And we have liquids, we have gases, we have lots of stuff. So let me run you from what I have been doing.
Yeah.
Okay, this is my first nuclear reactor. Okay, I think it's turned down at the moment. I need to clear that and the uranium here. Yeah, so this is also an attempt of salt reactor. So now the pressure is increasing. The heat here, which one it is? Here one, heat display. Okay, that should be increasing now in a second. See 100. So the color should be changing soon. There it is. It's changing now. So that is heating up now. Let me go with this one, with the fancy one. But it's taking a lot of time to. So this one, the first one that it maybe took more time. So let me help it a bit.
So are you actually using the water around the uranium as the moderator, or is that not simulated?
No, that's not simulated. I was trying to use it as a moderator or something, but no. What it's doing there is to induce pressure, because the game will see the water vapor and will increase the pressure on the chamber. And then this pressure on the chamber will, by increasing, it will activate the uranium.
Okay, and what is holding the uranium? Is that the heat thing?
Yes, this is the HIC, the heat pipe. It's destructible. It's the only thing that can hold that, practically, either that or diamond. And it conducts heat very well to extract the heat out of that.
Heat.
So here it is. The salt is being melted. We are getting started. And now the heat will traverse up and begin melting the salt here. And when there is enough energy stored, they will be starting to release the salt overboard.
So, but you're not creating water vapor then yet?
No, here I'm not creating water
Gotcha.
vapor. It's only dropping it overboard. And it all failed. You see? Total failure of the nuclear reactor.
Oh shit. Yeah, that doesn't look good.
No. So yeah, that was the first attempt. Then my second attempt has been much better here. But there's also salt being tossed overboard. Then there is the 2.1. This one, we could see it working, this one. Or maybe, let's pick the latest one, just so I'm clear. Yeah, this has an attempt of converting water to water vapor. So let's introduce some water here. Hope that my machine doesn't die in the process.
What is the yellow material?
That I'm using as an insulator. It's not an insulator, it's called RA.
Okay.
But it's used as an insulator because this one doesn't burn.
Gotcha.
So yeah. So you see it's being converted into vapor. Fantastic. And the reactor is here on the left, is already running. Now let me stop the reactor. Let's see if I can stop it without dying in the process. So let's turn that off. Okay, that will release some of the pressure. Once we get a bit of the pressure off, so we don't blow up everything, I can hit the stop button. I hope that now I can. And that will release even more pressure, and it has communicated the pipe here to cool down the reactor as well. So that will stop the reactor now. Takes a bit, but it's also not very slow, so it's fairly okay. Also, my walls are melting right now. See here, my walls are melting.
That's suboptimal.
Totally suboptimal.
Wait, and you can control this whole machine with 2 buttons.
Yes, I have a few buttons here to control it manually, or well, I have pistons for everything in this version. So I was playing already with pistons, some logic gates, not logic gates, but switches. I still don't have logic gates. I don't know how they work. But yeah, it's cooling down. It's cooling down. Now you can see in a second. I'll show you the startup sequence. Here you can see the salt is being teleported, so it appears here and it exits here. And then When it exits, it comes here, it drops, interchanges the energy, and then it teleports from here back to the top.
Ah, okay. Right. Yeah, it makes sense. Oh, okay. So and so the salt, the only heat exchange is the little orange knob at the top of the.
Yes,
Huh.
and some ambient heat as well. There is the ambient heat that this will spread a little bit of ambient heat, and it will sense via the ambient heat as well. But
Oh,
yeah.
yeah.
That's the the knob on the top is the main sense here. Okay, the reactor is mostly stopped. Okay. So the passing is full now. And we lost pressure. We have -2 bars, or -2 atmospheres. I don't know what this number is exactly. And the reactor is at 400 degrees and cooling down. Okay.
How are you turning off the? Yeah, what are you technically doing to stop the uranium?
I'm opening this here. I'm opening the enclosure. So the titanium prevents the pressure from leaking. So by removing it and opening it, the air can move outside, and that relieves the pressure. Once the pressure is relieved, the reactor stops.
So the pressure can move through.
Most materials except titanium.
Oh, really?
Yeah. So far, titanium is the only one that I know that can do this.
That explains so much. Right.
So now I'm going to do the start sequence. So you'll see that. Look, now the water has liquefied here. Now we have liquid water here instead of vapor. So now it's hard blue. Okay. So now let's try to start it. I click the button. And you see, this is closing. We are closing all the exits. That has been disconnected. It's no longer connected here. So we are not cooling the reactor either. And this here is creating plasma arcs and heating the element. This is a resistive element basically. And the heat is traversing inside. This traversing inside towards this wire to the reactor to heat the water. The water heats, gets into vapor, and the vapor is pressurizing the chamber. Okay, and it will keep doing this until we hit the melting point of the salt, and it will automatically stop. So right now it's automatically running it without my intervention.
That's nerdy.
About now, this should trigger here. There is a temp sensor here that will trigger at 900. So now it will start triggering this. This is triggering now, and that marks the end of the start sequence. Now we are stopping the resistive element, like the Tesla coil, the electrodes that were doing this. They are stopped, and the reactor is moving by itself. And now we are already creating some vapor of water.
Oh, so you were heating the water vapor all this time?
Yes, I was heating the vapor all the time to get into a critical state where we have enough pressure.
Gotcha.
Then, I mean, there is a lot of trickery here. So, for example, here, all these curves here is because I need the titanium to hold the pressure, but the titanium cannot get even close to that wire. So the only way is to make curves to make the air a harder path to exit. So it doesn't touch the titanium at all. It doesn't affect the titanium, and there is insulation in the middle. But because of the ambient heat, it also leaks. So that's why I'm doing this. And the same reason here is all retorted to prevent the air from escaping. Okay, and we are getting criticality, so the salt is getting whiter and whiter, meaning that it's hotter.
Mm-hmm.
Here it's getting whiter, and this is creating more and more But the thing is that, well, this is creating a lot of particles, a lot of water, and is not the design that I would like, right? I would like this to be smaller, more efficient, and the salt here, I would like it to convert it into solid salt, so to reduce the temperature to 900 degrees before returning it, to make the full interchange, because right now it's not interchanging the wall energy in the salt.
Right, yeah.
Okay, this is the current limitation that I had so far.
Yeah.
So then is when I jumped into doing the heat exchangers, like just this part here. Sorry, those are from the internet, from my hard drive. So in this, here is the idea. So I place basically a reactor that is already running at full speed and teletransporting the salt out and trying to convert it into vapor and expel it as soon as possible. And then the salt is being spawned here. So if I pause the simulation and remove the salt, there are the yellow dots. Those are a clone. Those are in here, in special clone that duplicates the particles. So as it goes, it's creating more and more salt.
That's how you generate new elements.
Yes. Okay, yeah, that's how I generate also here the water. The water is being created by the clones.
Right.
Okay, and the teleport is there is one single dot for the teleport here. It is connected here to the blue, like in Portal, right? Red portal, blue portal, so it's the same stuff here. So yeah, and here we have it running. Problem is keeping the symmetry, that everything I do on the left, doing also on the right. So the right side has been unattended for a long time. So the left side had more stuff ongoing and is doing more cooling than the right side. And yeah, I mean, it is cooling a lot. It is cooling a lot. In here, I mean, this salt is 9,000, almost 10,000 degrees. And just as it gets out, it's already down to 2,000 degrees. And when it exits, 1,200. So, I mean, that's quite good. We just removed like 800 degrees from the salt.
No.
So yeah, it's quite good. Not bad. But yeah, they still uses a lot of particles.
Right, I see what you mean, yeah.
And it's very big. So yeah, I would like something better. I was trying more stuff. I was trying this. And in this one, so the schema is slightly different. We have the salt coming out from the top, and then it spills down until it exits. And here is where I'm just removing it. This is called the void. This is this thing that will drain away any particle. So any particle entering just disappears. That's it. That's what it does. So
right, yeah.
So I was telling you before, Yarmo, so the idea is that in the future, this should have another portal out and portaling into the reactor, back into the reactor. Because that's what the clone is emulating right now. Because I'm testing, like I don't need to do it correctly. I just want to prove that it works. So here, with a particular shape in the middle to try to create the correct draft, so they get drained in the right way. So the idea is that the salt is exchanging the heat with the heat capacity here with the wall. It's exchanging the heat. So we have here 3,000 degrees, and those are 2,000 already when it comes out. But here in the reactor, it's at 9,000. So it's already losing a lot of heat when it comes out. But then as it goes down here, for example, 1,300, and in here we have like 400 degrees, and now 370 degrees. Okay, so it's losing energy as it goes.
Nice.
Then the wall as well heats up as it goes up. So the water is not being boiled off very quickly. but the water that gets boiled off goes up, and it will have a tendency to go up against the wall. And as it does that, it will heat up. And as it heats up, it will encounter a wall that is even hotter. Because this one is 1200, 2000, and almost 3000 degrees. So the idea is that the exit point here, this exit, so the water is exiting here at 3000 degrees, okay? So this one maybe is using a lot of water that is not needed, but you see that there is not that many particles that are exiting the game arena. There is just a few bits of particles, and that is enough to remove all the heat from the salt. This is the key thing. I don't know. This one is quite good. I'm very happy with this one. I don't know what you think.
Yeah, it looks really cool. So why are you using diamond instead of the Heek?
Yeah, I had to come to that conclusion as well, because like a lot of my designs were not working, and then I thought like the problem I was having is that the Heek was placing almost the same temperature on top as on the bottom. There was almost no gradient. That was making this water to be boiled off very quickly, and the salt to exit much hotter. Because let's say that we just replace now with the Heek. It will mean that this part here, instead of being at 200 degrees or 300 degrees, it will be maybe not 3000, but will be 2500 on the bottom, and the salt will be being output very hot, and the water will be boiling off here at such a speed that it will exit super fast, and in the end I'm not getting what I want. So the diamond is creating a heat gradient. Let me see if I can show you the heat display. Yes, so it's creating a heat gradient, and I'm using this on purpose, so the vapor is heated gradually as it exits. So to guarantee that, so because all that I don't need to exchange it as soon as possible. What I need is the water vapor that gets out, it needs to be as hot as possible, and this is the point. It is getting out very hot. This is what I want.
Yeah.
I don't need to pull a lot of water. I need to, whatever I pull, it needs to be very hot. This is the whole point.
Okay, so the Heek was actually too efficient in.
Yes, it was too much.
Huh.
It was too much in this case. So for this design, diamond works better than Heek for this particular design. So for the objective of removing the heat from the salt, to cool it down, it's working better, this design.
Right. Yeah. And what is the thing on the right bottom doing?
Nothing. This is just for a test. To test things like, for example, adding water vapor. So this is for me to just manually give it a try, fill it with water vapor, and see what happens. See if the water vapor goes the other way, or if I can cool the salt just by adding water vapor. It's just for testing purposes.
Gotcha.
That's it.
And the spawning again happens with the clone thing.
When in here is a teleport. It's a teleport because here is the problem. Clone can only this clone can only create particles that you can create with a brush, and the problem is that they cannot spawn with a brush salt that is at 10,000 degrees. So the only way I have to spawn the salt at 10,000 degrees is to preheat it and then teleport it. Is the only way. So that's why there is a reactor in all of those, just for the sake of getting the salt heated properly. But yeah, this reactor has no way to do a startup or a turn down. It goes 100% all the time, non-stop.
Cool. Yeah, and yeah, so much stuff to learn. Yeah.
So yeah,
Okay, yeah.
this one is nice. I did a few tries that were total failures. Here is this one. Let me remember what was this one. Oh yes, here we have spawning directly vapor into a chamber and working against like there is probably a teleporting here that we cannot see. Here are the blue dots. It's teleporting in here the salt. And now we have a wall here for gas, so only the gases can pass through. This will be the water vapor, and then it gets stuck. And as it cools down, it drops down the salt. Salt just falls, and then I have another wall here to drop only the salt, not the water. And then the salt is the one that's discarded with a bit of water as well sometimes. So this is an interesting design, but still I don't like it, the way it works. Tons of particles again, and just placing it in vapor also it doesn't seem the right thing to do. Also tons of vapor being poured in. So then I was looking into this one, which is refrigerant. I thought that like, okay, what happens if I put refrigerant in here? Which is for the, as you were asking me before, like when you do a compressor and so on for fridges to cool down stuff. Was trying to use it because it has different properties and it can exchange a lot of heat, that's true. But at the end, I end with the same problem, which is like I need to exchange it yet again with water, and then we end with the same problem. So I was like very disappointed. I don't get anywhere here. And now this is the 4, and now we have the 5. This is my current version, and I'm much happier with this version.
Okay.
Okay, so we have a water reservoir here. This white thing here is creating pressure, it's a vent, so it's adding air pressure over here, just to force the water out, because there is pressure here in this chamber and I need to pressurize it. Your keyboard arrived all here and is even less responsive than the current one? What? Is the one with cherry black? That cannot be right. That cannot be right. It's really a cherry black one, or did you get a scammed or something? I mean, the cherry blacks are a bit harder to press than the regular ones, but... Yeah, I know, it's the one from eBay, I know, but I don't know. Oh man, that's sad. Okay. Oh man. I'm sad. I'm very sad for you. Yeah.
What kind of keyboard was this supposed to be?
He's looking into a mechanical keyboard.
Alright.
But yeah, they are hard to find. Yes, good keyboards are hard to find. I spend a lot of time researching to get mine. A lot. A lot.
And what are you working with?
It's a Corsair. Which one it was? Give me a sec. Maybe I can. EK70 Lux. It was. Yes. This one. It's a K70 Lux with cherry MX Browns.
Nice.
It's a good keyboard. It's a good keyboard. I have very little complaints, if any, with this keyboard. I'm very happy with it. I don't know if it is still produced. Maybe not, but probably there is another model that more or less fits. But it took me maybe 2 weeks to filter all the models and find this particular one as I liked.
Yeah,
tell me.
I've had two. So I've had the N Pro 2, which I was very happy with. And right now I'm using one of the Keychromes, which I'm also very, very happy with. It's actually a German build. Yeah, I think it's a German company, yeah.
Uh-huh. Yeah, there are a lot of good keyboards. It's just that it's hard to filter them across with all the other keyboards that there are. Everything has some minor thing that I don't like. Because I wanted a Spanish layout. I think a Spanish layout that everything is English layout for mechanical keyboards. And the other thing was I wanted a full keyboard. It's the other thing, and I wanted cherry MX brown.
Yeah.
I didn't want the reds. I didn't want the blues. The blues are super common, and the reds are also super common. But other than blues and reds, the other switches, both, is not that common at all. So yeah, finding it in Spanish plus brown switches, it was very hard. But then I'm very happy with it. It has the tactile click that I like. It's not noisy. I could put O-rings myself onto the keys. I could customize it a bit to my taste. Nice. And it has another thing. It has a second USB that has a USB socket, a plug that I can put my, I don't know, another device. So the idea for this will be to plug your mouse onto the keyboard, for example. But what I'm using it for is for UV keys. I have UV keys for work, and I have also my personal ones. And then I can just plug the UV key here on the keyboard and touch on the keyboard instead of having to reach to the computer. That's quite nice. Also, the other thing, it has light, but it's not RGB, because I didn't want to have software for RGB in Linux. And it's red, because I only want red, because red is very easy on the eyes, especially by the night. So I want the lighting to be red. Only red. So
it shouldn't work at night.
It's not for working at night. It's for playing at night.
Oh,
and doing stuff at night. It's my keyboard for everything.
Fair enough. Yeah,
of course.
You're right.
Of course. So yeah, so I don't have any kind of drivers for this. It's just that I plug, it works. I want to change the amount of lighting. I have a button to change the amount of light. That's it. See, I don't know if I can show to the camera. Okay, let me change quickly. I don't know if I can do this without. Maybe what I can do is move the camera down. There it is.
That's way too red. That's very red, man.
Yeah, that's with the minimum. The camera is not able to adjust. That's the minimum.
Yeah.
Let me see. I can do that. Yes. So you can do more redder, or not at all. And I have it at the minimum. Have it just that minimum is fine. I mean, in real life, it doesn't look as red as with the camera. The camera is basically blooming it all. But yeah, the keyboard is nice. So yeah, let me show you how this thing works. So let's disable that temporarily. Let's remove that and put something over. Okay. So we'll stop it. Okay, and now the water vapor is getting out. So you see that we are basically filling in this thing. So if I remove, you can see that it's filling this tank. But just up to certain level. One thing that this game is not doing is leveling the water from both tanks. So it will reach the point here when it goes upwards, and it will stop. It doesn't account for the pressure from the water. That's a pity, but it's what it is. Okay, so now that this thing is full, let's say that we put a bit of salt into it. Okay, the salt will go down, will touch the water, and it will boil the water, and at the same time it will convert it into regular salt, and it will drop down. Okay, so we can recover this salt. Now there's something interesting. See that there are two colors of water. There's a lighter water here.
Yeah.
This light water is salt water. It's because it's mixing the salt with the water and it's creating the salt water.
Ah.
Okay. But it reaches a point where this salt water is starting to boil, and it will boil off the salt as well. So we also recover the salt from here. Okay. So this creates the steam, and you can see here on the top that the exit is quite small. But also, I think it's this one. Yes. So also there is quite a lot of heat. I mean, yeah, 1200. So this 1200 degrees is exiting the device. So that's good. So the trick here is that the hotter gas also will rise. So when this thing is full of water vapor, the vapor that is hotter also will tend to raise as well. And because the vapor that we just create, it must be also colder than the upper water vapor, because this water vapor is also exchanging with the salt. It's mixing with it. So it's becoming also hotter, therefore goes also up, where this one is colder. So it's creating the same kind of transition that we are transitioning from cold to hot, and making it exit the hottest part possible. So that's good, and we don't have a lot of water vapor going on. I mean, it's same amount of, I mean, it's still 43,000 particles, but I think we can make this smaller. That's why I think, not sure, but I think we can make this smaller.
Yeah. And so why are you using like direct heat exchange now? Why are you not doing the a diamond tube now?
Because I think this is simpler than the diamond tube, because it's creating the same effect in less space. The other one was way bigger in width.
That's true, but like this is not like it looks very messy, because yeah, you get this. Oh wow, it's getting messed up now.
Yeah, now everything is being vaporized, but also the salt is being all converted into salt, back into the dust, into solid. But it will regularize eventually. It will become normal because now it's pressurizing. We are getting more and more pressure. Once the pressure gets back to normal, it will drop down. Yeah, you see, we are getting water already. And we are getting more and more vapor here concentrated. And it still works. It's quite amazing. I can try to close this gap, see if I can get more. If I can get more flow. Yeah, now I'm getting more flow. Okay. So now the challenge is how to get more flow of salt here, because there is a difference of pressures that it's hard to make right. But yeah, that's way more salt that's being discarded here. You see that there is no salt water anymore? There is no way to get salt water because it's being boiled off. So if I had added salt water, we got the salt out already.
Right, yeah. Wait, I don't get the little thing that you did there. You changed the gap size. How did that influence the whole system? I didn't get that.
Yeah, and now it's stopping now because of the pressure again. So it's because it was stuck here. Let me reopen. So it was getting stuck here because it was trying to get out from here. And that was a problem. And now the problem is that there is not enough pressure here on top and too much pressure on here, and the difference of pressures is preventing it from creating a draft down. So the salt is becoming stuck on the top and it's not.
Oh.
And now it's being drawn down, but you can see there is a blob here because of the gap.
And that's just with the gap. Holy shit.
That's just with the gap. So if I remove the gap, the blob goes away, but now we get the other problem. Maybe I can create the gap lower? Maybe? Maybe we get the best of both worlds if I have the gap lower. Ah, that's good. It's not such a big blob that it's not impeding the exit. It's... Yeah, that's good, that's good, that's good. It's not filling up. The top reservoir is not filling up. So this is working at full speed now. Yeah, the direct exchange is way faster because you have a lot of more surface area. The small salt particles with small vapor particles have a lot more surface area than the other heat exchanger. Plus, it uses also the same rule of heating up progressively as it goes up, by also exiting super hot here. So it is exiting.
True. It looks very messy. Sorry.
Yeah, it looks messy, but if it works, I don't like that it's hard to see what is happening. I don't like that. That's also why I was looking into the refrigerant, because in the refrigerant, at some point it was looking clearer. You could see the salt dropping and interchanging and so on. The problem is that I had no way to make it work efficiently, and then it was becoming even messier than this. So that's what I came with. So you see the salt blob here on this right wall. It's also because of this gap here. Is the pressure being dropped in this side?
Oh wait, what is that part doing?
It's pulling the particles to the right, basically to create a draft, so the water has a better chance of entering. So it's lowering the pressure of this chamber.
So it's a gap just like the other one then?
Yes.
Okay.
That's just to control the pressure. Like we have also another gap here below to lower the pressure from the bottom. So that's all to reduce this pressure here. Here is 25, 24, 23, 22, 21. So the problem is that we are creating too much pressure. So with all this exchange and vapor creation, we are creating a ton of pressure. And the other problem that what I don't like of this current design is that I have to create pressure here on top manually by adding a vent, just to push the water down. That's the part I don't like. So I would like to be able to inject the water in a cleaner way. So I could, for example, try to remove this and see what happens. So we remove that. We start dropping the pressure here, 28. And then, if I'm not mistaken, at some point the water will not drop. the amount of salt that is converting is amazing. But now you see, we are lacking water here already. This is still working because there is water coming in and changing into steam. But the gap, look there. There is already a problem here.
Yeah.
It's not going down.
That's weird.
Yeah, and now it goes again. It goes in phases because the elements like water and other stuff, it doesn't block the pressure totally, but there is some pressure being blocked slowly. So there is a bit of pressure drop. So when it's full of water, it's dropping the pressure and it's creating kind of a valve. It's blocking the air here.
Right.
And then when it goes away, then it should equalize at some point and it should go again. But now you see that the salt here is still in liquid form because it's orange. Still in liquid form, very close to the grid. We continue, we'll start getting liquid here, and that's very bad. It's gonna destroy the engine. That is a failure already on the process.
Yeah.
So that needs to be fixed. So let's fill that with water to help it a bit. But it's already too late, I think. No. Okay. It's working. So a theory could be like, okay, what if we put here a gap as well? And we open the gap here. Can we prevent... No, now it's not entering at all. We put the gap, now the water is not entering at all. And we are getting vapor in, and that's very bad. Should not get vapor in. So that is the problem. If I, for example, we can in tools and add air manually and put air here. Let's put a ton of air. More air. Come on, more. Okay, that's maximum pressure. You see, we are okay. Now is forcing the entry. The problem is that there is so much salt that there is not enough space for the vapor to get out.
Yeah.
Of course, the vapor that goes out will be super hot. Yeah, 6,000 degrees. It's super hot, but not enough. Not enough is getting out.
Yeah, so but that's the messy part, right? That's because you mix directly.
Yes, because I mix directly. Yeah, exactly.
This is where the glass or the diamond tube would save you, but yeah. Huh.
Yeah, we could try to... another problem is that with so much pressure, this thing is not going down, you see? Now it's being blocked totally. I need to remove that, and still, it's being blocked. The salt is not going down. I mean, in this situation, it's good because the machine had too much salt, so it's good that it's stopping until it cools down. But that should not happen. So the problem with the other way of mixing, let's say, okay, let's put another mixer here. So we copy this. Okay. We have a full wall, so we don't affect one system with the other. So this is another system. Now I can open this. Okay, so there is the salt. The salt creates a draft because it's hitting the air. The air is going up, so sometimes it goes up. Okay. So that's fine. The problem is that the air will eventually heat up. And yeah,
Oh.
yeah, there is an ambient heat at some point. I mean, it's exiting as well the air up and down. So I mean, we could also interchange with air as well, no? But the whole point of this is also to create electricity, because when you do this exchange, the point is to create electricity.
Yeah.
To create electricity in vapor or anything, no? You have here this thing, a detector. This is just to simulate your electricity generator. So you can put the detector over here, and then you can run a cable, maybe with titanium, I hope. Like that. No, that's to wait. I need to put the actual insulator here, or we will be messing up a lot. 1 pixel is enough, because this yellow stuff with electricity, it is very bad, the result. So I need to isolate it properly. And now I can do this. Yeah, and that's creating electricity. So, but I mean, this doesn't count the heat or the pressure or the speed of the particles, so you could use it with anything. So it's nothing realistic. I cannot count how much electricity I'm doing, because the game is like either there is electricity or there isn't. There is nothing else. Energy is not conserved, or at least not in electricity.
Right. Yeah.
So I could, for example, put it here and say that, I don't know, I can make something funny here, no? And you could say, yeah, there it's running and whatever. Okay, so you can draw something here just to make the idea of that it's running. So that's the whole point. That's the whole point. That's why the exchange with air is like, yes, you're producing 10,000 degrees just to throw them into the atmosphere for no particular reason. So the whole point will be to actually get energy back. So with this, let's try the diamond ones. Here, special diamond. Let's remove that, and let's do something like this.
I'm trying to recreate your reactor here. My computer.
Yeah, that's what happens with this game. It's just addiction. Okay. Now we can try to do something like this. Okay. Now with the clone, we're going to say that around here. Hey, Slicer, hello, welcome. I'm here doing nuclear reactors and heat exchangers with Yarmo. Okay, let's put water here. Okay, so
what button is it to fill a whole area? Was it?
Shift control at the same time.
Shift control, thanks.
Shift control. Okay, what temperature is this going out? 3000? I mean, not bad. Not bad. Now, for the real thing. What happens if we open... I mean, let's do something like that. so it doesn't. No. Wait. I want to give it more room. So I want just to the side. Something like that. Okay. Hey, hello. Happy St. Patrick's Day for you as well, Tomiluko. Okay, so now we are throwing more salt. Way more salt. A bit too much. And now it's vaporizing everything, and this is not working that well anymore because the clones cannot output water. You never heard of this game? Me neither, until Slacers told me. So, yeah, this game is an engineering trap for me. I'm just stuck in here, trying to do machines, trying to do nuclear reactors and everything. Okay, let's put a bit more space. But yeah, the basic problem right now is that we are overpowering it. We are overpowering the amount of cooling.
Right, yeah.
I don't know if it will help if I put a bit of insulator here. Because that might be cooling down the particles, so we want just hit the particles. I forgot about them, but it is totally overpowered at the moment. So yeah, now what? I mean, this is not now it's totally overpowered. Okay, stupid idea. Let's duplicate the system with another one. So heat exchanger for the heat exchanger, because why not?
Hell yeah.
I mean, that cannot go wrong.
I mean, it does make sense.
And I want this one to actually create water. Maybe the problem is that maybe if it is overpowered already, I cannot do anything about it. So let's try to fill it with water first. Let's see if I can cool it down a bit. To see if it helps. Because the whole idea will be if we can... Oh, you know what? No, but it's a ton of... I mean, I could connect them here. But the problem is that the water levels do not share in this game. They are not shared. It makes sense, but now... This stream is colder, right? 3600? 7000. This stream is colder. We don't want that. We do not want that. We want this stream to exit as hot as the other stream. Which means that this one needs to go... Oh, that's ugly. That is ugly. That's ugly. I need to join the channels. Something like... Ah, that's big. Need to join the channels and force them out together. Here is the other problem. This part over here, we want it isolated. We don't want to exchange with this side of the wall. Okay. Now they should join. We should do the exchange in the late part. Okay, okay. That's getting out super hot. Everything, all the stream is getting out at 8,000 degrees. That's not bad. That's not bad. The problem is that all of this is at the same temperature. That is a problem. And all the part below is at the same temperature. So now what do I do here? maybe if I kept inclination all the way through. By the way, the setup on the left is totally... This is totally fucked. It's full of melted salt. Okay, let's clear the part of the left. Because we don't need that anymore.
How do you kickstart your reactor?
Oh, let's do that now. Okay, and
because I think I built it like you do, but
okay. Let's do that in a sec. So let's remove all parts. No. Now there is nothing. Okay. Why are you here? Floating like... No, don't float. Don't float. I hate when this happens, when you have the particles there everywhere mixed together. Ah, crap. It's a mess. It's a mess. Okay. So for the reactor, you pause the simulation. It will be easier with the simulation paused. Now, you pick uranium. Forget about the others, polonium and so on. Uranium. You get a big brush size. Okay. Place uranium. Now you go to solids. Heat exchanger. A bit bigger circle. Okay. Now you need water. So bigger circle. Okay. The next part, you need to go for insulator. So electronics, insulator, and bigger circle. And now the last part is the titanium to hold the pressure. So the insulator will protect the titanium because that's so hot that the titanium will melt. So that will prevent the melting. Okay. Now we can start the simulation. Sorry. In my simulation, the ambient temperature is too hot. I need to cool it down. Okay. Wait. Still hot? So, in my case, it just started by itself. Wait for a second. Let's see. Because I also have pressure, so let's reduce the pressure. It's still water vapor. There is still ambient heat. It keeps pressure. Why it's water vapor? Because the lack of pressure. Okay. That's fair enough. That should be. Could do. Property. There is. No. No. Let's do it roughly. Come on.
All right, you get it going as soon as all the water is water vapor.
Yes.
All right.
Yes. So what you do is basically either you inject air or heat. You inject heat. At the moment this thing is above 100, it will kickstart by itself. Inject air. And that's it. Once this has like pressure 4 or pressure 6, it will go. And now it's going. Okay, so the water vapor is for that. It's for keeping the pressure, the container pressurized.
Yeah, I was building one and I kept on heating the water, but it wouldn't kickstart. But yeah, of course you need the water pressure. You need the water vapor, not the water.
You put the water and you heat it until it vaporizes. Until it basically converts it into vapor. So over 100 degrees or 200 degrees, and it will become vapor. And then it's done. You have it already. The way I do it here, because I want salt, I can replace this with salt. But only if it's only salt, hidden powders, salt. It usually takes more time to start. But the salt also pressurizes when liquefies. The problem is that it takes like 900 degrees to make the salt liquid. So usually I have a layer of water vapor and then another layer of salt. That can be isolated by the heat exchanger if you want, for example. Okay, the next thing is the teleporter. The teleporter is here in the special. Then particle in can go here and put, for example, I don't know. You can make a line, you can make a dot, it doesn't matter. You put it here. And now the thing is that the portals have channels, and they depend on the temperature they are set. They don't change the temperature by the surrounding ambient. So can come here and say property drawing tool temp 450. Usually I go for because the channels are in increments of 100, so channel 4 is from 400 to 500, so I center it in 450, and then I draw here to put this all at 450. And now if I do portal out, that I put here, you can make it different length, doesn't matter, or even split it into halves or 3 halves, that doesn't matter. By default this is now 25 degrees. Whoa, wow, what happened here? It broke down. Interesting. Never happened this to me so far.
I'm only seeing it now. Holy shit.
Yeah. Why? Oh.
Oh, you're burning the... Oh? Yeah.
It was the space. Having the space... Ah, yes, this insulator burns. So if you leave a space, so it's not burning because there is no gap for the fire. But as soon as there is a gap, it will burn entirely. And very violently. That's why, for example, instead of this one, sometimes I'm using this array that doesn't have this problem. The problem with the array, I'll show you in a second what it does. This one, if you have a gap, there is no problem. It works perfectly. This one I can put the portal out. Yeah, okay. And then for here, let's put even 3 gaps in here, doesn't matter. So it doesn't work because it's in different channels. This is in the 22 and this is 450. So what we do now is here, property drawing tool 450, okay, draw 450, and here you go. All the salt out. All the salt is out now. Okay. Now to make this continuous, you just get the clone to put fresh salt here. You can, for example, put it here like that. Sorry, no, I don't want... No, I want the clone. clone, like that. And now you put the salt, powders, salt, and then we will create salt at all times, and the portal will remove the salt. So this hits the salt, this removes the salt, and we have the salt here. Okay? Now this container needs pressure. I'm pressurizing right now, not with titanium, I'm pressurizing with the outer shell, which is this thing, the wall that blocks everything. That's a bit cheating in this case. But yeah, to create two different sections that don't exchange information, that don't exchange anything, it's good. But yeah, the problem, like, it's grabbing a lot of salt. Even the clones also sometimes they work faster if you have less clones, like separating them. They tend to work faster if you do that. Something like that. We could even put more clones so we get faster fill rate. Here you go. Now it's quickly full. So yeah, that's how it works. So now I can, for example, remove all those portals, put just 1 pixel. And there it is. Okay, the problem now is that we are not outputting enough vapor, basically. It's not enough pressure, in fact, to make that air get out soon enough. So we can use titanium to increase the pressure here. But the titanium, of course, it will melt. So we need an insulation layer. Now it's when it's becoming messy. And then a layer of titanium. There is not enough insulation. Either that or we have the ambient temperature already too hot. Yeah, it's too hot. Cannot put anything there at the moment. Ooh. Super hot. So I need to create a draft. Let's create a draft in a different way. Let's put a fan. Fan that goes up. Okay. Another problem is that I'm affecting the salt. And now it's not mixing properly. And even the water vapor doesn't want to get out. Like, no, get out. No, get out. Doesn't want. It doesn't want. I mean, I'm reducing the amount of air of temperature in the outside. Not anymore. So yeah, I have a problem. I do have a problem. I don't know how to do this. Remove the fan. Now it falls down. This thing goes up. Okay. Can you refrigerate with water? Ah, you can see the chat, sorry. Yes, in fact, this is water, but it's being converted into vapor all the time. So, I add the water, and it gets converted into steam straight away. Look how much water I can add, and could open here. And see, this is the original problem. Like, how much water do I need? And this is still too hot. So yeah. Now what? Now what? So, for example, here we could say that when it reaches this point, we already lost it, because when it goes down, we don't really want to be exchanging more energy at this point. So let's keep that off, give it a bit more space. And now let's try to remove. No. Let's try to remove here a bit of. No, come on. When you want this to cooperate and really doesn't. So here I could put a bit of insulation. Yeah, something like that. Up to the end. Remove that. And now that. Fill. Run. Okay. Let's try to cool it down. Let's see if we can get regular water here. Come on. Doesn't want to cooperate. Okay, let's reduce the flow again. I cannot handle it with that amount of flow. So you see that it's a problem. Yeah, Sam. This is a game. It's called the Powder Toy, and it's free. You can play this for free. You just have to download it, search on the internet, the Powder game, and it's very easy. So, easy to download. The game is not easy. Depends if you are going to find it fun for you or not, but it's very nice. So yeah, so here is the problem. Like the amount of surface area here is less than before, way less. If I could get some pressure, if I could pressurize the container, that would be amazing. If I could pressurize the container, because water boils at a higher temperature as the pressure comes in. So if I put a container, okay, thank you all here. Let's remove this wall. I don't need the wall. Wow, now everything is flying away. Eventually it will settle down. Eventually. But yeah, I was saying, like, if I could get pressure, the story will be very different. And I need a bigger insulation wall. It's better than vapor? No, it's the same. It is the same. The problem... Ah, okay. Thanks. It's the same on insulating. The problem is that the water is coming from here. This is the main problem. It's coming from here, and if there is vapor around it, it will not spawn any water, so it's not getting filled. Okay, I'm going to exit Mumble because if I'm alone, what is the point? Okay. So that means that we are not getting more water in because it's full, because it finds no place to put the water, so it's not spawning it. This is the problem. This is the problem here. So still at 1000 degrees. I mean, I could inject it instead of like that. We could try just by sheer pressure. We could try to inject the water like this direction, for example. So like making a wall here for only liquids. Now let's just pressurize it. Titanium. I don't like this wall like that. Let's make something nicer. A better curve. I don't know. It looks ugly as hell, but I hope that it's more effective. Now the idea will be to clone the water here instead. Could you guide the water far from the heat source with pipes or something? Yeah, but the point is that I want to convert the salt from liquid into solid. But as I convert into gas, it will go up. I lose control of the gas. And now let's put pressure. So something like this. Let's see. Well, that's a ton. That's a ton of pressure. But yeah, it should work. We could do this to get the pressure up. So it will force the gas out. I hope. So let's see. Okay, we're getting more water. But still I'm lacking now. I'm losing the pressure over here and it's flying away. All this air is flinging the particles away. Yeah, I mean, it's not bad. It's getting the water in. But the problem is that the pressure needs to go around here. I mean, we can cheat a bit to understand how it works, so I can use this kind of walls. So okay, that is a bit cheaty, but for now, let's call it good enough. Yeah, I know. You mean the part here, the output. Yeah, but this is what I started with, having a bigger outlet. But the problem that I have with bigger outlets is that I need a lot more vapor to get out to have the same effect. Okay. Okay, I almost have water up here. Okay. Okay. Now let's try. Let's try more load. Okay, not bad. I can close this like that to prevent the drafts from happening. I mean, not bad. I'm going to save this as the 6th version of this. It's the titanium is melting. Ah, no. No, don't do that. Okay. I mean, we could put it higher or put another one higher here. Now we get double the output. And now we are not. Now it's not extending enough. And the problem with making the throat, the end throat bigger is that we'll lessen the contact with the wall. And I need the contact with the wall. Oh, come on. This thing is melting away. It's melting away. Wow. Save it again. I think pipe coil could increase the surface area. Like a serpent. But I mean, this is 2D. You cannot do this. You cannot. I mean, you could do a zigzag, but then once I turn left, once we down to the left, then you will not have the salt on the other side. I mean, we could emulate something like that by adding a lot of teleports from one side to the other, but yeah, it's not optimal. It's not exactly optimal. 4,000, 4,000. Yeah, other problem that I have is because it's 2D. I have a lot of problems because of that. I mean, in this state, maybe the problem is the throat is not big enough. We can see in the heat display. Yeah, I mean, we are not exchanging it enough here. Yeah, a few particles are coming out this heat, but not all of them. And the throat is quite small, so if I make the throat bigger, we will see is that we'll get better output. The heat is lower. So we're getting more volume out, but at a lower heat, which defeats the purpose. That is why I was going for the other type of interchange, where I was mixing the vapor with the salt, because the salt has the salt has a lot of more area than the pipes and these tubes, and also the water vapor itself. So both together interconnect with a lot of surface area, extending a lot of heat. That was the advantage. I mean, we could do also, I don't know, exchange it with another material before going into water. So, for example, there is mercury. Mercury can mix well. But then I cannot mix it properly. I cannot separate it because this is liquid as well. It will be hard to separate later on. But mercury here, it settles. We have less, let's say. Doesn't go down. It doesn't want to go down. I thought like mercury will be a liquid that is denser and it will go down anyway. Where were you putting the salt? What do you mean? Where I was putting the salt? Like the idea is to get the salt out of the reactor, pull it down, and then put it back again. So teleport it back again to top. In the design, I'm not doing it that at the moment, but that's the intention. So the point is that the salt needs to solidify in here. There is the gel here. It's also liquid. And in here, everything else, yeah, snow. Of course, I call the output snow. That's also, I consider that cheating because snow comes at 0 degrees. I don't find that realistic. And sand does melt into glass, and glass will get stuck into place. So it doesn't serve a new post here. Powdered quartz. The problem with powdered quartz is that it melts and when it cools down, it becomes proper quartz again. So it's only useful above 3000 degrees. And then it will deposit and will solidify. This is a huge problem. Clay dust. Does that become it's combusting? Ah, it gets molten. But I'm not gaining anything from that, I think. And these produce a paste with water, which solidifies. So sawdust floats on water, nice. But this basically burns into fire. So that's not useful. Powdered silicon. And that remains powder. It remains powder. And then here yeah, it is a powder. It's not moving, but possible to create a system. Okay, in a second I'll be back. And I'm back. I'll make myself louder, a bit louder. Okay. Yeah, more or less. Okay. Let's Okay, so this is using silicon instead of salt. Okay, let's just to test. So question is if it is easier to exchange this with water than salt. I mean, it has different properties, it solidifies much quicker. For example, let's say that I put a no, no, I want air. Yeah, it's still a powder. This is still a powder. I can cover that. Yeah, but anyway. That is not my question anymore. Let's remove this. Oops. I want to remove the portal out. Okay. Now let's use the amount. Okay. And let's see how it behaves with water. Water. Yeah, it is settling to the ground very quickly. So here's the transition. If I'm not mistaken, this is the transition. So the one. So molten silicon 31, silicon 31, salt 200. Yeah, around 3000 is the fusion point when it changes. But still, it floats a lot. This is my main complaint. It is affected a lot by the air. And the problem is that I want you to go down and vapor to go up. Now the vapor is getting in. Come on. All those liquids. Oh. So here. Okay, another more here. Come on. Okay. See, it's not going down. The vapor, just the pressure pushes it up. It's like, no, that's not what I want. That is not what I want. There was here for accelerator. What is it doing? Or Juro's repulsion, maybe? Instead of this. So I want to speed it down. I don't know how. And this starts to sound like cheating, you know? Okay. This is starting to look better. It's getting up with the... This is the same problem as with the exchange with the salt. It has eaten. Oh, that's salt. Oh, interesting. It has eaten through all the water that I placed here before. Marvelous. More force, please. Yeah, that's super violent. Why am I getting salt? Is this salt? Oh, this is salt. It's not what I want. I want to test. it was the silicon dust. Let's see if I can. Okay. Okay. Now we have a bunch of silicon here. That is. Okay. But yeah, for the direct exchange, it's the same problem. The same forces. It's creating here a vortex. Let's see. Hit display. Yeah, I mean the trick, no, the tricks. Where you were putting the salt? The salt wasn't in here, so here the idea is that this reactor normally has salt that gets molten, and this salt is coming here. But now I'm changing with silicon. I wanted to put here. Let's see. Block the air pressure. Including over there. But even with that, it's just creating a huge tornado of vapor depositing the ceramic over here. The silicon. There should be a better way. Yeah, the silicon is already warmer than the any water they can put. We put water here, it will vaporize straight away. This is too hot. But it's not that hot either. I mean, here, yes. I don't know how to make this work properly. Could just try to bring this down, maybe. Remove the wall here. Okay. Then bring it straight down. maybe let's say we are not mixing them. Let's say that it just goes straight down. Past that thing. What happens? Okay, that's qualified. I mean, it pulls down, cannot go anywhere. What happens if we remove the force? Will it still go? Yes. Okay. Can I remove the walls that I placed? Does it still work? Okay. What is the temperature here? 500, 600. But I think that's the same with salt. I don't think we have anything special with this one. That grants that. See, the problem, if I can get cool it down enough so you can have liquid water, it's much easier because just to pour the water. You just need to cool it down. Yeah, this powder is much more sticky than the salt. It may look better, that is under more control, but I'm just removing less heat from the reactor. So this is moving slower, more slowly. See, if I put water here, the water also goes down. No, but yeah. Then the vapor goes here and it screws everything up. See, it doesn't seem to be better than the salt. Getting tired. I need to close very soon. And what I wanted to maximize is the output here of the particles. That still 400, only 400, just a few that are very hot. I mean, we could still deflect them. You want them hotter? You want to make them hotter? It's just a matter of we push the particles against and then we push them away. Like we do something like this. And that will exchange the heat. Yeah, now it doesn't. If you pull it down too much, it doesn't flow. It's more problematic than the salt. So let's remove this. Let's remove this. Remove that. Let's remove this wall as well. So it doesn't get stuck. Okay. Now it's totally exchanging the heat. Yes. No, maybe. Just keep adding water. And as long as it's not full of water vapor, it will keep putting the water and renewing the cycle. Here, yes, we are exchanging all. We are, yeah, putting the particles as hot as they can be. Which one is this? This one. Okay, the problem, yeah, so far, let's save it. Now the question is, can this design work faster? Because that's not enough salt for the reactor to work. So this, no, this goes here, this goes here, this should be open. Now can you copy that, paste, okay, the output, okay. Now can you keep it up, because this is a lot of heat. Oh, that salt is not needed. Yeah, the problem now is that because it's vaporizing everything, now we are losing the cooling capacity. There is no new water coming in. So it's being maxed out. And still there is 50% of the particles that are not being heated up. And this is a problem. Those outside particles, they need to be heated up. So one way to do this is to add turbulence or to contract the throat in here. Press them together. Somehow they need to be pressed together. Problem is that if I'm pressing them together with material, the amount of particles getting out will be less. Hotter, less particles. Simple solution is to put vents. Simple. And yeah, I mean, you're getting more transfer out. So maybe it's even cooler now a bit, but not really. Another way, allow gases here, for example, to dump the extra vapor that is being accumulated. So it can be dumped. This is suboptimal, totally. And still, I'm not getting enough contact over there. This is the problem. When the system gets overwhelmed, there's no way. Is it a good idea to push the water towards the salt pipe? Yes, ideally, yes. That's what the throat is trying to do here. I mean, yeah, I mean, we could do... Let's try that. Sorry, mistake. On this one. Air vent here. Air vent here. That's a lot. For the sake of testing it. Can always remove, right? Yeah, well, I mean, that is way too much. Because now the salt is not flowing. The salt should flow. So much. Okay. Goes here. the pressure normalizing or what? Are we just dumping all the water? Okay. Let's try removing here a bit. It's way too much pressure. Yeah, I mean, I think that it's simple. I'll give you that it's simpler. But it's not currently working. The one with the pipes was working very well. It was doing a lot of work. This one so far. Okay. You know, the salt is going down. Here there is the interchange. Is being overpowered. I'm thinking that I don't want the gas to be let out, so let's put the barrier. At this point, what we are going to end up doing, if I continue doing this, is basically a circuit for forcing the water through. That's not what I want. What I want is that naturally the whole system enters into an equilibrium where it does the job itself without having to add a lot of energy, because all those vents are adding energy. You could divide the central pipe too. Divide the central pipe? I don't get what you mean. Wait, that sounds like that design that I had. But it's working like this better. Let me show you. I don't know if you saw it before. This design. Seems that this is what we are trying to get at. In the end, we will get into the design. Don't remember what happens if I overpower this one. What happens if we get way much flow rate than this? Okay, let's see. Does it overpower or it runs properly? It runs properly. This one is quite good. It's one of the best so far. Might be the best depending on your taste. One of my best designs so far. There's a bit of a trick here that I'm adding pressure here in this point. I don't know how critical it is if I don't add any pressure, if it will fail catastrophically or not. No, doesn't seem, so far, doesn't seem to be failing. Which one it is? Fire, heat, I mean, heat, yeah. There is a few cold particles in the middle, but it looks good. Can we? Yeah, why not? What happens if... So what's the center? This is the center point. What happens if I do that? And now the output is hotter. Not losing much performance, if any. Not bad at all. I could use this design. I don't know. It's one of the best so far. I could try to redesign it and try to make it shallower or something. I don't know. It's just very wide. I don't like it. It's very wide. Being tall, I'm fine with it being tall. Big wide, I don't like it. It uses so much space in the screen. Need to be closer, sorry. Let me show you again. I don't know if you were here before, but I'll show again my reactor. Oh. This on the left is my nuclear reactor project. Let me just stop it quickly. and I'll show you what it is. I showed it at the beginning of the stream, but I will repeat again because also I'm going to go to sleep, so before I go to sleep, I'll show it again. It should be cooling down. Yeah, it's cooling down now. So what I'm trying to do is to replace this heat exchanger. That's what I'm trying to do. This needs to be replaced. This is so big and so inefficient that it takes a lot of particles in the game to process all that heat. That's what I'm trying to change. That's why I'm so focused on doing this. Okay. It just stopped. Let me cool it down a bit more, so I can show you more or less from stop. Okay, so I have electronics here, so I can do where are you here? So I can control. Yeah, I was trying to do all at once, but I was confused, so I tried to do just the right part in a different file to understand what is better. So, for example, let me, I'm trying to optimize exactly. So this part over here, this has a cooling rack here. This is for cooling. This is kind of the emergency cooling or the stopping cooling. This is for basically for stopping the reactor. And it's currently connected here by this red heat pipe. And I can disconnect it. I can do that and disconnect it, or I can do this and reconnect it, which is the state. Okay. The other one here is this door. This is a door. If I hit here, the door is moving, and now what this is doing is closing the recipient here. So this is the reactor and needs to be closed to gain pressure. Okay. So this door is opening and closing, so now it's open with a heat exchanger as well to cool the reactor, and now it's closed, so it keeps the pressure in. Yeah, I mean, I made this myself, right? This is basically the piston, and this is a bit of material that I used. It's not a piece. It goes pixel by pixel. I designed that myself. And this one is also this is the main chamber for depressurizing the main chamber. So you can press here and then it closes, so allowing the pressure to stack in. Or you can do that, and it opens and the air can get out. This is the main thing. So if I hit stop here, it triggers all at the same time, and start triggers them all at the same time as well. Then here we have the starter. The starter consists of electrodes that will create an arc. Here, you see? It's an arc with plasma, and the plasma is super hot from the arc, from the plasma arc that is created. That will heat this part over here, which is the heating coil, let's say. Okay. And this heating coil needs to heat up, and the heat will come in here through this snake, and it will arrive here to the reactor. And this will heat the reactor, heating the water, converting the water into vapor, and when it converts into vapor, it will expand and it will create pressure. And with this pressure, that will be added into the chamber is what will trigger the uranium into starting producing heat. And after that, it will be self-sustaining. So when I do this, but of course, doing this manually, you need to hit that for a long period. So what I do is I hit the start button once, and there is an automatic system that keeps running the starter coil, until it hits, I think it's 900 degrees in here. There's a sensor here, this big thing is the sensor, and if it's 907 degrees, it will trigger and stop the starting sequence. Yes, it's meant for starting the reactor, and it's also what keeps the reactor going. If you remove the pressure from the reactor also stops. So you need pressure to get the uranium going. So now this is heating up. We get already water vapor. We can see on the upper right side of the screen the pressure going to 7.7, 8. Okay. We are melting already the salt, and we are getting some vapor in the chamber on the right. And now the starter has stopped already, because we have already enough temperature, so now it's sustaining itself. How did I learn all of this? Because I spent way too much time on this game. I only knew about this like 2 or 3 weeks ago, so I'm a new player. I just started. I was looking into the there is a wiki that explains all the parts. I had to look part by part and trying stuff. So trial and error and reading a lot of documentation. The same way as the software works. So that's what it is. So now you see, now it's working alone, and it's gaining more temperature. So we are already on 2500 degrees and raising. We keep raising because the pressure is building up. As it heats, it creates even more pressure, and it becomes self-sustaining because the heat is what it creates more pressure. So the uranium with pressure creates heat. The heat also creates more pressure, and this pressure in turn creates a feedback loop with more. How do you connect some sensor? How does the know when to stop? Because there is something called here Wi-Fi, that here comes the signal from here. Okay, this is the cable, and reaches the Wi-Fi. The Wi-Fi has a channel. Here is the minus 250, and arrives here, which is the minus 250. And there is a switch here that, depending on from which material you spark the switch, you can stop the switch completely. If you spark from, because there is the positive part, there is the p-type silicon and the n-type silicon. If you spark from the n-type silicon, closes the switch. If you spark from the positive side, which is the bottom part, it enables the switch. There is a battery here that is trying to push the electricity across the switch. So that's how it works. So this is signaling. Yeah, it's more like a relay, like a transistor, yes. It's like a transistor. And this thing is always creating more and more heat. 9700 degrees, which is more or less the maximum. But as you can see, I cannot exchange all the energy with the water. You want to give it a try? Yeah. Search for the powder toy. It's free. The game is totally free. I think it works on Windows, works on Linux. There's also a version for Android, but I don't think it works very well. I didn't give much of a try. But yeah, it's quite basic, but it has so much stuff to try. And those are reactors. You can well, like uranium reactors. You can do also deuterium reactors, deuterium neutron reactors. You can do lots of stuff here. Limit your imagination. And the knowledge that you have, of course. But you need a lot of knowledge here. You need to study a lot. But yeah, it's worth it. It's worth it. Now the problem is, if I want to stop the reactor, if I press the stop button, this is a defect I still have. I will correct. Yeah, exactly. It's very rewarding. If I press the stop, if I press the stop, it will open this gate here straight away, and it will be too early. There is too much pressure, and will overheat everything. You see? It's overheating over here, overheating here. And this can cause a meltdown. Was trying to avoid it, but it's causing a meltdown here. See? Meltdown incoming. It's too hot, I cannot disable the reactor in time. See? It's melting down here. It's melting down. And right now, I mean, the reactor was not so much pressurized for it to fail spectacularly. But let's say that we have even more air. Yeah, let's use it one harder. So let's put more pressure. More pressure. More. 200. Yeah. That's way too much pressure. So now we have too much pressure in the reactor. And now, if you attempt to disable the reactor by opening everything, we'll get an instant Chernobyl. Here you go. Total destruction of the reactor. Wow. Oh well. You want the Chernobyl, right? Yeah, totally destroyed. So, what I have here, with the how it works, is like this escape can be used to depressurize it slowly. Can do this. No, just still too fast. Can do this. It's still okay. One more. It's melting. Okay. And now it's depressurizing. But you need to wait. It will depressurize. So I cannot open this hatch more until it depressurizes. So I need some logic to control this, because I have props to read pressure and limit the amount of movement that the stuff can do when trying to stop. To do always a control stop, that would be amazing. Ensure that the automatic stop is always correct. Okay, I can try a bit more. To pressurize faster. Like that. Okay. Now we are only using this hatch to depressurize it. We are not using the bottom one. And once I reach, I don't know, 25, I guess, or 20, should be good enough. I mean, there is still a lot of pressure. So just by going slower, just by depressurizing slower, you can prevent the meltdown. So it needs to start slow and to stop slow. You cannot shut it down quickly. Yeah, I mean, in reality, yes. In reality, you have control rods. In the game, I don't have control rods. That's not how it works in the game. So now I can hit stop, can open everything, and now this hatch will pressurize it even faster. And this spot will cool down. Still, it's getting very hot. I need probably to refactor this part. This is probably one of the first parts of the reactor. That's maybe needs a better way. But yeah, it's getting red hot, but we are still between margins. Now that this is open, we get negative pressure, so we only need to remove the excess heat. So, I mean, I could remove the excess heat just by placing ice, for example, in here. Can you create some control rods as you did with those pressure? Yeah, but the thing is that that's not how the game works. So in reality, you will be absorbing neutrons. That's what you will do in reality. So you will put control rods that will absorb the neutrons. But this uranium in the game, it does not get the power from the neutrons. It gets only the power from the pressure. So the only way to power it up or power it down is to increase or reduce the pressure. That's the only way. There is no other way. I would really like to have control rods. Seriously, I was looking into other radioactive materials because there is here. This, for example, polonium that gives off the neutrons. Okay, gives off neutrons and it decays over time and it heats up as well. But this one, I mean, I'm not sure if more neutrons will decay faster. In the uranium, no. In uranium, you don't have decay material. Polonium decays into neutrons, so this one disappears. So this material creates neutrons and disappears, it says. What is this material here? Polonium as well. So this one doesn't decay, but the other one, plutonium, does decay. But plutonium decays into uranium. So plutonium, you put it next to the polonium. Here you go, you see? And you get explosive, massive reactions because when it hits the neutrons, it creates heat and uranium. So maybe the solution would be using plutonium, and this one does decay. Well, it decays into uranium, but yeah, it's way more reactive. Maybe that's plutonium. I need to test more stuff from here. I don't know, like I add neutrons. Yes, too many neutrons, and it just explodes into molten polonium and other stuff. And there is the other thing. Water, which is also from the real life. Water does moderate the neutrons. Neutrons slow down in water, which I think in real life this is used to speed up the reaction. Slower neutrons have more chances of reaction, and we can see here that we're getting we are getting heat out from the polonium. Interesting. Yeah, the molten material is very hard to handle. That's the problem. And the polonium is getting expanded. I might need to research this more, because it seems that this type of reactor is possible. But like if we get, okay, let's say only polonium. Okay, with lots of neutrons. Okay, and now we get water. Distilled water. It is reacting along with water into molten polonium. But it's not very hot. This is not very hot. It's reacting. That's interesting. Let's add more pressure so the water can stay liquid for more time. Come on. Come on. Maybe? I haven't checked if I have a material that absorbs neutrons. Probably. There are materials that do reflect neutrons, but absorbing neutrons? I don't know. I haven't checked. I haven't found anything. Okay. The polonium is getting gray, so I guess that this is a waste material, like this is a spent material. But it looks like the polonium, the main usefulness is to create neutrons. And then when you get the neutrons, you need plutonium that will react with the neutrons generated from the polonium. And it will create a lot of heat. Okay. I mean, you know what? What is a really molten salt reactor? A real molten salt reactor. Let's see. let's say, molten salt reactor is something like, no, but doesn't have water. Molten salt reactor. So let's say, okay, regular reactor. We have water. Okay. Here's our water. Let's close that in. Let's close that. Molten salt. Salt, you know. Salt is obviously water. So molten salt. So it's a reactor that works with salt that is molten and is mixed. I'll show you in a second, but I don't think in game we can do that. Let's see. So we put plutonium. I need to close this. Okay. So plutonium. We add plutonium, and now we add polonium, which creates neutrons. Okay. And this. Okay. 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 And we get the reaction. The problem is controlling these and the right sizes. This is more or less how a real reactor should work like. Then you need these materials in some sort of control rods, like control rods. No, in a fuel pellet. So you need something to store them. So they have a particular shape. So probably they will be both mixed together, both things mixed together properly, and something like a ceramic or something to hold them together. Counting that they will not melt the ceramic, hopefully. So in reality you will have something like that. And then you will have a bit of polonium. And the remaining, I guess that will be plutonium or something like that. And yeah, it destroys everything. Because it's very hot already. It reacts with the okay. But it's melted already. So if I here add just a teeny bit of plutonium. Okay, it doesn't react. Bit more. Okay. I get energy back. Yeah. That would be the idea more or less. Maybe we need some material to moderate this. As you were saying, Because I think so. You have neutrons. I mean, ceramic, it's because it's not very hot. Ceramic holds up to 2600 degrees. Plus, it increases a lot with temperature, so it could be nearly 3000 if it is under a lot of pressure. It's the best material that you have that is not a cheating material. If you don't want to use diamond, if you want to use a realistic material that can melt down, ceramic will be probably your best bet. Thinking, look, go. In reality, what is used for neutron moderation for absorption? You said carbon alike. Let's go first with this one. Yeah, here they just bounce up. That's not what we want. Carbon alike coal. That sounds like a very bad idea, but I mean it's carbon alike. I don't think that's gonna work. I mean, they exchange something with the carbon sometimes. There is a chance. A gas. Noble gas. Oh, yes? Is that the answer? Wait. Let's use a container just to make sure that I'm not. And let's use a spawner to make sure we. So now you spawn neutrons. Okay. Now, if your theory is correct, then I add noble gas and I slow down. I remove the neutrons. Yes. They absorb neutrons. That's a good call. Noble gas. Oh. It's spinning. It spins. How can I tell? Okay, so you have to look at the density of neutrons that you have. Yes, I created a tornado. Yes, that's true. Wait, I'm trying to remove all the gas. Wait, I can do just this. Okay, I remove all the gas. So you have to look at how many neutrons do you see here at any point. So, because they have a life and the amount of bounces that are allowed. Okay. Then, I don't know, let's fill it totally with noble gas. You see? There. If I remove a bit of gas, yes, no, not like that. It finds a gap, you see, the neutron shoots, but it dies. Now, why did I get a tornado? I have no idea. I don't know, it was that random. Maybe I think there is too much gas. Get enough neutrons to do the work. I could add more neutrons manually. Yeah, they apply a force. They apply a opposing force to the gas. No, they apply a force, because they apply a force, it has a tendency to turn. Yeah, look, it's filming again. Interesting, eh? Yes, that's the source of the neutrinos that matters, yes. Oh no! Oh no. It's weird. But it's just that it can be reproduced. So yeah, maybe it's a mixture of neon and water, because water has the opposite effect. Water does... Oh, it makes the water liquid? Nice. And slows the neutrinos. It exchanges with the neutrinos, slowing them down. Wow. Because okay, neutrinos increase the pressure. That's why the water is becoming liquid. So the water will make the neutrinos more powerful because they slow down, and the neon will make the neutrinos die before. So you could control the speed of the reaction by those two terms, I guess. And that would be a regular reactor. Then you will need to exchange the heat from the reactor out without having a meltdown. I will have to try that at some point. I am tired already. Then, before I go to sleep, the molten salt reactor that I was saying. The idea is... I don't think it works in the game, by the way. I don't think this works. But the idea is, you have salt, and then you put your radioactive material into the salt. Whoa! It reacts with the salt already? That was unexpected. Because uranium doesn't react. Polonium does react? No, it doesn't. Does it? No. I mean, I don't know, maybe the salt is doing something because this is creating so many neutrons. But I don't know if part of this is the pressure. Is the pressure... Because the whole idea is that a molten salt reactor does not have a pressurized container. The whole idea is that the pressure is small. Yeah, the salt is creating a better with the neutrons. Yes, which is helping, but I wonder if it is doing something else. Okay. We don't have it. So yeah. So the thing is that molten salt means that it needs the salt to be heated up to the melting point at least. So it needs to be melted. Come on, come on, come on, come on. And then with the salt melted, you have, well, I guess we'll stay melted for a while. Nah, don't solidify. Okay. Then they mix the material on the salt. Let me try a bit. Okay. Yes, but I needed to keep it. The idea will be keeping it melted. Ah, it says here. No, okay, no. Generates neutrons under pressure. Ah, because it was pressurized the container. That's why it seemed to react. Now there is no pressure, so it's not generating neutrons. Yeah, I don't think this works in the game, because in reality you will have this dissolved into the salt, so it will become a single thing, a salt that contains plutonium, or I think it's thorium in reality. I don't know, it might be uranium or whatever, no? But it will be dissolved, and then it will be reacting inside of the salt at the same time, so it will basically heat the whole salt, keeping it liquid. And the cool thing about that is that it does not require high pressure to work, because the salt does not boil off. It doesn't create a lot of pressure. It creates a very small amount of pressure or no pressure, so it's much safer to work with, and it can become much more efficient. Yeah, well, something like that, yeah. Something like that. So we have here the salt that is molten, that's being heated by the plutonium, uranium, whatever, that is being reacting, and then you pull out the salt, and then you cool down the salt, like it's happening now, and then you will pour the cold salt back in to reheat it again. How would you control the temp? I'm not sure exactly how the temperature control is done in molten salt reactors. Either by controlling the density, because you pull out the whole liquid that contains the uranium, not like in here. And you can add more salt or less salt, I guess, but probably also from the outside. I don't know, it depends on the material and how it reacts. In here, the plutonium is creating neutrons under pressure. Because this one... I mean, the polonium is being melted. Is this what I want? It is very pretty. It's very pretty. Molten polonium here, but while the molten phase here in the game, it doesn't seem to be much plutonium. Oh, here we have polonium. The polonium has got out because it was melted, and then it's creating the neutrons outside. That's a pity that it doesn't create neutrons while inside, or does it? No, it doesn't. It doesn't create neutrons while molten, only when it's cold. That's the pity. Yeah, just the heat. Just the bare heat of the salt is creating the pressure, yes. But in here it's funny that all that a lot of neutrons here. There is not, I mean, two pressure. Yeah, yes, the salt is creating the pressure, yes. Wait. If I just grab salt, so here there is no pressure. Now I do this, and it settles. No, this game it doesn't create pressure just by weight. But when it's liquid, it seems to create pressure. I don't know if it's just by the heat. That heat equals pressure or something. And salt, molten plutonium? Did I read that correctly? Salt rock. Molten polo, I don't see it. Oh well, it's very pretty, but I don't know how to use this in the game. So I don't know. I cannot mix it with the salt. It settles down, so it becomes unusable. Try to use water to try to mix it. We mix it. Come on. No, it doesn't want to mix. And it's getting colder. I mean, we have other stuff. We have also exotic matter. The stuff that we can do reactors with. So yeah, I mean, with the game we have a lot of choices to have fun with energy. Electrons. They don't seem to be doing anything. And protons. Wow. And photons as well can be used. Like the electrons, I think they go with this one, the exotic matter. And it can be also used to make a reactor. Okay, that's awesome, yes. The exotic matter is oh, what just happened there? I had a bunch of exotic matter and it disappeared. What? It disappears like crazy. What? It converts into a different thing? It freezes. This is new to me. In here is normal. No. Freezing as well. No, but... No, this is correct. But in here? It doesn't drop? Now it drops. Okay. Now it disappears. What? Electrons. Okay, that should like activate it. So when it that explodes, come on. Yeah, okay. I guess that I cannot extract the energy as like in a bomb. I cannot make a bomb easily like that. Oh no, okay, that's melting the salt. Very colorful. We have also gravitons that can pull things. Can I pull things here? And there are singularities. That it's the stuff messing around already. I have no more energy to spare and I need to go to the bed. Oh well. Anyway, that's all for today. Thanks everyone for coming in. Hope you liked it. Because if you like, I don't know, I can stream again this game later on. Because I enjoy it a lot. Well, see you. Have a nice day or good night, depending on where you are. Bye.